Okay, since all matter has mass and takes up space, it can be characterized by a property called density. And density is equal to the mass of that matter divided by the volume of space that that matter occupies. So that means it has units of mass in the numerator, which is grams, and units of volume in the denominator. And that volume kind of depends on whether or not we're talking about the volume of space occupied by a solid. Oftentimes then our unit will be centimeters cubed. Or if that volume is a liquid, we might have grams per milliliter, which is a unit more associated with volume of liquids. One really important conversion factor or relationship between these two is to remember then that for every 1 centimeter cubed you have a mil. That's a really useful conversion factor to use when converting between these two types of units. So we also, in terms of characterizing the matter with density, that the more dense matter is, the heavier it is. So we're getting at whether or not things would, for example, sink or float when they're put into water. For our purposes, density is going to function as a conversion factor. It allows us to make relationships between the mass of the object or the matter and the volume that that matter occupies. It allows us to go back and forth between those two units. So let's take an example here. Let's say I have a metal block. So some block, it's made out of metal, and it has a total mass of 235.87 grams. And my metal block is a cube, or maybe it's a rectangle, and it has dimensions of 2.1 centimeters by 3.2 centimeters by 4.5 centimeters. And I'm trying to figure out if this block is made out of iron or lead. And I know the density values of iron and lead. So the density, measured in grams per centimeter cubed, of iron is 7.8 grams per centimeter cubed. And the density of lead is 11.3 grams per centimeter cubed. So I need to figure out what this metal block is. I know its mass already. That was given in the problem statement up here. And since I know its dimensions, I can calculate the volume. So the volume of a cube is length times width times height. So I could fill that in as 4.5 centimeters times 3.2 centimeters times 2.1 centimeters. And if I do that math, I get 30.24 centimeters cubed. Now, I haven't rounded yet because I don't like to round my answers until I get to the final calculation. So if you save your rounding till the end, then we'll round to the same spot based on significant digits. So now that I know the mass and the volume, I can calculate the density of my metal cube. So I take the mass, which was given to be 235.87 grams, and I divide it by the volume, which was 30.24 centimeters cubed. I get a density of 7.79993 grams per centimeter cubed. Then if I look at my sig figs here, since this is a division problem, I've got 4 sig figs in the denominator, and I've got 5 sig figs in the numerator. So I should have 4 sig figs in my final answer, which means I'm going to round to this position, but I have to use that 9. So if I number off, I get the density of my unknown cubed to be equal to 7.800 grams per centimeters cubed. Therefore, that's what this little triangle means. Based on the densities of the known elements, I know that my unknown cube is made out of iron. So let's do an example now where we utilize density as a conversion factor. So let's say we know that the density of gold is 19.3 grams per centimeter cubed. And I want to know what is the mass of a sample of gold that has a volume of 5.0 centimeters cubed. So I know when we're doing conversion factors, and in this case we're going to try to convert from our volume of gold to a mass of gold. So we're going to convert from volume to mass. So we're going to start with the number we're trying to convert, which is the volume. So 5.0 centimeters cubed. And now we're going to use density as a conversion factor to convert that volume to mass. So since I'm trying to get rid of centimeters cubed, which is my volume unit, and go into a mass unit, I know that I need centimeters cubed on the bottom because then it will cancel out. So I'm going to put my mass then on the top. Then I'm going to go back and fill in the numbers. So I know from my density that there are 19.3 grams for every 1 centimeter cubed of space that gold occupies. So if I do that math, I then get 96.50 grams, which if I round that to the proper number of sig figs, would be 97 grams of mass. So that's an example using density as a conversion factor. We can also use density as a conversion to convert the other direction. So in this example, let's say instead, I know the mass of gold, it's 10.0 grams. I want to know the volume instead. So now I'm going to convert from grams to volume instead of from volume to mass. But we still start with the number that we're trying to convert, which in this case is 10.0 grams of gold. So we're going to use the density again, but this time, since I'm trying to get units of volume, that's going to go in my numerator, and units of mass will go in my denominator, because now when I multiply, those units of mass will cancel out. Then I'll go back and fill in my numbers. So I know from the density that there are 19.3 grams in 1 centimeter cubed. So if I do that math, I get 0.5181 centimeters cubed of volume occupied. Rounded off to proper sig figs would be 0.518 centimeters cubed. So in this case, I flipped my conversion factor over in order to convert from mass to volume, unlike the last problem where we converted from volume to mass. So in our last example, I'm going to take a look at what if you have an irregular shaped object. So you don't have something that you can easily measure volume by taking, for example, length times width times height, or a cylinder where you know it's 4/3 pi r cubed. Actually, that's a sphere. But instead of specific shapes which have equations for their volume, what if we have a rock? So a rock looks like that, has no specific shape. And let's say we know it has a mass of 5.0 grams, and we want to calculate the density of this particular rock. How much space does it occupy? In order to do that, we're going to have to measure its volume by displacement. So that means we're going to figure out how much volume that rock occupies by figuring out how much volume of water it displaces. So the way we do that is we put it into a measuring device called a cylinder. And a graduated cylinder is a tall glass cylinder with measurement markings on it. And we'll look at some of those more closely in the homework examples. So you fill that graduated cylinder with water. And let's say I measure that, and I find, when I write down my measurement with my last digit as an estimation, that there is 1.82 mils of water in that particular graduated cylinder. Then I'm going to add my 5-gram rock to it, and it's going to displace the water. It's It's going to take up some of the space that that water's occupying. So if I put my little rock in here, it'll sink to the bottom. And now the water level will actually be higher than it was because the rock has displaced some of that water. So let's say the water level now is at 2.64 mils. If I subtract those two volumes, I find that the rock displaced 0.82 mils of water. Therefore, that's the volume of the water, and I can now count the density of the rock by taking its mass divided by its volume, and I get 6.1 grams per mil. So that's how we can calculate volume by displacement and get the density of irregularly shaped objects.